All right. Yep, there it is. So, section 11.2 is when we actually take probability and start using it. Um, this video is going to be pretty short because uh, a lot of the slides are kind of like talking about actually trying things and writing down probabilities. So we'll just kind of hit on the highlights of this real quick. Our EQ is how can I use simulations to model experimental versus theoretical probability. Okay. So just a quick warm up, let's figure out if each situation is a permutation or a combination. And remember, a permutation means that when we're choosing things, the order in which we choose them matters. And a combination means it doesn't matter what order you pick them in. All that matters is do they get picked or do they not. So 20 students are competing to be one of three to move on to the final round of a competition. And that key phrase is to move on to a final round. It doesn't matter if you're first, second, or third. You have the same outcome. You are moving on. So that's a combination. You are arranging your movie collection on the TV stand. Now you might say to yourself, I don't care what order that the movies are in on the TV stand, but anytime we talk about arrangements, we're talking about visual differences. And if you were to take two movies and switch them around, that visually will look different. You might say to yourself, it doesn't matter, who cares? And I would actually kind of tend to agree. But if you see that word arrangement, we're talking about a specific ordering of things. And so that is going to always lead to a permutation. And finally, you are choosing three numbers for a lottery drawing. So most lottery games, you can choose the numbers that you want, the numbers that you think are the winning numbers. All you need to do is get them right. It doesn't matter the order in which you say them. So a combination would be the correct answer here. Just get the three right numbers. It doesn't matter if you say which number first. It's just, did you get them right? Okay. Here's one that we're going to skip because we're going to actually do this in class. This is an interactive spinner. But how many fives should we expect to get in 6 spins? Well, that spinner's got 6 sections. They all seem to be equal in size. So reasonably, if I were to spin that 6 times, I should get 1 5. What we're going to do is we're going to do it in class and see if that actually does happen. Because it could be, right, it could be 0. I could spin 5 all 6 times. But this is where we talk, and we'll talk in a second about theoretical versus experimental. In theory, I should get each number 1 time. It's probably not going to happen, but it should occur. That's theoretical. This is experimental. Experimental probability is something actually occurred, or I'm keeping track of an event that actually goes on. So the probability of some given event, okay, let's say what's the probability that I roll a 5? What's the probability that I make the piece of paper into the garbage can when I throw it across the room? Okay, so the probability of an event is simply we write as a fraction, which then we can turn to a decimal or into a percentage. How many times did that event occur? That specific event that you're looking for, divided by how many times did you try, or the number of trials. Okay, the larger value has to always be on the bottom, right? You can't have an event occur 10 times, but you only tried 8. So when we're talking probability, the denominator does always have to be larger than the numerator is. And we can write it as a fraction or a decimal between 0 and 1. So 0 being it did not happen, and 1 being like 100%, it happened every time. It will happen again. So again, just reiterating, experimental probability is based on something that actually happened. You can see it. You have evidence to support the experimental probability. Okay. Again, here's one we're going to skip. If I roll those 2 dice, 8 times, how many times will I get a 6? And it's actually a kind of an interesting problem to talk about experimentally, It's an interesting problem to talk about theoretically, but we're going to actually run this experiment, so it's going to skip over this. How many times should we expect to flip heads if I flip a coin 8 times? Now, a fair coin is considered 50-50, right? Half heads, half tails. You have an equal shot of those two things happening, assuming it's not weighted or anything crazy. So how many times should we expect to flip heads in 8 coin flips? It should be, right, in theoretically, it should be 4 heads and 4 tails. Now, is it going to be 4 heads and 4 tails? It's actually pretty likely that it's not going to be 4 heads and 4 tails, but in theory, it's a 50-50 shot, so it should be half and half. So we're going to actually run that experiment and see what that looks like. Okay, here's an experimental probability or an experiment that I can actually put numbers to. So Desiree and Jeremy are shooting free throws in the gym. Desiree has made 18 of her 43, and Jeremy has made 29 out of his 67 attempts. So Jeremy has shot more and he has made more, but that doesn't necessarily mean he's a better shooter. We have to apply the numbers to this. So who has the higher probability of making their next shot? Now, all we can base that on is what we've already seen, right? If you watch basketball, a player's free throw percentage isn't like in theory. It's we've tracked how many they've done and they've made this percent, so that's their percentage or their chance of making the next one. So for Desiree, okay, she has out of 43 trials, she has tried 43 times, she has hit on 18 of those. Now, fractions are tough to compare, but decimals aren't. So we're going to go to the, oh boy, come on. Please don't. Okay, so we're going to go to the calculator, and we're going to say 18 divided by 43 is 0.418, which we could then write, if we wanted to, 0.418. If you want to think of this as a percentage, is 41.8%. And I can change a decimal to a percentage by just sliding that decimal point to the right 2 times. So Desiree has made 41.8% of her shots, and she has a 41.8% chance of making the next one because that's that's her success rate thus far. Jeremy, on the other hand, has made 29, but he's shot 67. So we're going to, again, go to the calculator. 29 successes out of 67 attempts is a 43 point, we're just going to say 43.2. It would round to 43.8. But so here, this is 0.43, 432? Yeah, 432. It would round to 0.433, not 432. 0.432, which means Jeremy has a 43.2% success rate, and that is his probability of hitting the next shot. So who has the higher probability of making their next shot? That would be Jeremy by just a little bit. Okay. So that's a classic example of experimental probability because you are tracking stats for someone. It's the same thing in baseball with batting average and ERA. Really with batting average. Almost all sports, right, they keep track of some stats and then you compare to figure out what their probability of success is. Again, lottery time, something that we'll do in class, so we'll skip this for now. Theoretical probability, as we kind of touched on already, that is the probability that something occurs without us actually running an experiment or running trials to see if it happens. So very similar setup, but we do introduce some new language here. So the denominator is the number of possible outcomes. Just how many different ways could something happen? Okay. So if you're rolling a dice, the number of possible outcomes would be 6 because there's 6 sides to that dice. That's what we call the sample space. Okay. The numerator is the number of ways that a certain event could happen. And that event is what you're trying to find the probability of. So if I said, what's the probability that you roll a 2? The numerator would be how many 2s are on that dice or on that die. And there's 1. That is what we call the event space. Okay, so we have sample space is the denominator, or how many outcomes you could have, and the event space is how many ways can a specific event happen. Okay, so there's kind of that theoretical probability. Oh, look at that. If you throw a number cube, or also known as a die, dice is the plural, what are the probabilities of the following? So all of these are going to start with over 6 because there are 6 sides on a die. And then if we can reduce the fraction, we can reduce it from there. So what are the probabilities of that I roll an even number? Well, think to yourself, how many evens are on that die? We have 2, we have 4, we have 6. So of the 6 sides, 3 of them would result in a hit for the event that I'm looking for. 3/6 would reduce to 1/2, or 0.5, or 50%. Okay, any of those things would work. What's the probability that I roll an odd number? Well, of course, if there's 2, 4, and 6 are the evens, then 1, 5, and 7 are, 1, 3, and 5 are the odds. So that would also be 3 out of 6, or 1/2, or 0.5. Okay. What's the probability that you roll a multiple of 3? Well, on the die from 1 to 6, 3 is a multiple of 3, and so is 6. So this would, our theoretical probability of rolling a multiple of 3 would be 2 out of 6, or 1/3, which is 0.3 repeating. And what's the probability that I roll a prime number? Now, prime number is a number that you can only, it's only factors, or the only whole numbers that multiply to it are the number itself and 1. And so our prime numbers are actually 2, 3, and 5. 2 times 1, 3 times 1, 5 times 1, those 3 numbers, that's the only way to get, that's the only way to use positive numbers to multiply to. So 3 of the 6 numbers on a die are prime, so that is again 1/2, or a 50%, or 0.5 probability. Okay. Again, we're going to get into a bunch of different things, but those are theoretical probabilities. What is the theoretical probability of rolling a sum of 6 with 2 dice? So if I roll 2 dice, what's the probability that I add them up and I get 6? Well, the first die. Now let's attack it this way. I'm going to roll 2 dice, right? The first one has 6 different outcomes, and the second one has 6 different outcomes. The question is, what do I do with those 6s? Okay. If we think about, I could roll a 1 and a 1, I could roll a 1 and a 2, 1 and a 3, 1 and a 4, 1 and a 5, I could roll a 1 and a 6. I could also roll 2 with a 1, and these are different because they're 2 different die. I could roll a 2 and a 2, a 2 and a 3, a 2 and a 4, a 2 and a 5, and okay. So what I'm going to end up with is 6 columns with 6 possibilities in each. So that means I'm going to take these numbers and multiply them together. Okay, I'm going to take these 6s and I'm going to multiply. That will give me my sample space of 36. Okay, now we have to think, how many, for our event space, or the numerator, how many different ways could I roll a 6? Now, if I would have listed all those out, we would have seen I could roll a 1 with a 5. I could roll a 2 and then a 4. I could roll a 3, then a 3. I could roll a 4 and then a 2. Or I could roll a 5, then a 1. Okay. I can't, one of the first die can't be a 6, because then the other one would have to be 0, and that's not possible. So if I count the number of the number of possible ways for this event to occur, to roll a sum of 6, there are 1, 2, 3, 4, 5. So my probability is 5 out of 36, which I could easily change, because 5 out of 36 doesn't mean a whole lot to me. So if I want, right, we usually compare things in percentages, 0.138 or 13.8%. 0.13, technically that would round to 9, or 13.9% is the probability that you roll 2 die and get a 6. Now, the experimental probability would be different because it depends on how many times you roll the 2 die and how many 6s you get. So that is our theoretical probability of rolling a 6. Okay, again, just going to keep talking theoretical or a couple more things, and then we'll wrap this up. If you draw a marble at random from a bag, okay, so there's a bag of marbles. It contains 14 reds, 10 pink, 18 blue, and 6 gold. Find the probability of each of the following events. What is the probability that you pick one marble at random? Okay, I guess I could be a little bit more clear with this. You are only taking out one. So what is the probability that the marble you pick is not pink? Well, the first thing I need to do is add all these up. I need to take and add the 14, the 10, the 18, and the 6. That's 48. So there are 48 marbles in this bag. Okay. What is the probability that the one I choose is not pink? Well, of 48, 10 of them are pink, which means the rest of them would fit into the category of being not pink. So 48 total minus the 10 pink ones. That means 38 in that bag would fit my event out of the 48. Go to the calculator. 38 out of 48 is 0.791. And another thing I would do as you're doing this is just use the calculator to do the math, enter, so it can reduce the fraction for you. Because either answer, either form as a decimal or as a fraction is fair game to see on a quiz or a test. So 19 out of 24 or 0.792. So 19 out of 24. Oh boy. So 19 out of 24 or 0.792 or 79.2%. Any of those things are equivalent. Okay. What's the probability that is either blue or gold? So if I think about, I've got 18 blue and I've got 6 gold. Add those up because, right, it doesn't have to be both blue and gold. It can be either one because I'm only taking one marble out. So it's 24 out of the 48, which of course reduces to 1/2 or 50% or 0.5. Okay. So that again is a theoretical probability. Now, those are on the easier end of the theoretical probability problems. Something like this, it gets much more interesting. So let's say I'm going to deal you I'm going to give you 5 cards. Okay, 52 cards in a deck. I'm going to give you 5 at random. What is the probability that you have 3 aces in your hand and exactly 3 aces? Okay. So 3 aces and the other 2 are not aces. Most probability problems, it's easier to think about the sample space first and just like what's happening. Well, overall, what's happening is of 52 cards, I'm giving you 5. Now, what we do have to question and bring in 11.1 here is, does the order matter? Does the order in which I hand the cards to you, if it's the same 5 cards, does the order in which I hand them over matter? And the answer to that's no, right? It doesn't matter if you get ace then queen, or if I hand you queen first then ace second. Like, that does not matter. So of 52 cards, I have a combination, and I'm going to hand you 5 of them. Okay. So of 52 cards, I'm going to hand you 5. NCR 5. That number is 2598960. 2598960. So if you think about that, 2598960. That means there are, and a lot of card games use 5 cards. There's almost 2.6 million different hands that I could give you. And again, that's saying order doesn't matter. So that's a pretty significant portion. Our event space is what you normally have to do a little bit more work on. Okay. So my event is, I want the probability that I have exactly 3 aces. So that means I have 3 aces and I have 2 that are non-aces. Okay. So what we're going to do here is kind of a 2-stage problem. Let's first think about how many different ways could I get 3 aces. There are 4 aces in the deck. I want 3 of them. Again, I'm handing cards to you, so the order in which you get them does not matter. So for the 3 aces, of 4, I'm going to give you 3. Order not doesn't matter. 4C3, I type that in the calculator and I get 4. Okay, so that's for the first part. I'm going to move this over. And then the next step is, okay, that's great, but we have to make sure that the other 2 are not aces, because if one of the other 2 cards is an ace, now you don't have 3 aces, you have 4. So 2 non-aces, well, again, order doesn't matter, so I have a combination. How many non-aces in the deck? There are 48 non-ace cards in the deck, and I'm going to give you, not 4, I'm going to give you 2 of them. So I'm going to do 48C2 in the calculator. 48 math C2. So there are 1,128 different pairings I could give you of non-ace cards. 1,128. To get my event space, then, I'm going to take those values and multiply them together. So four ways to get 3 aces, and then each one of those 4 has 1,128 different ways to get the 2 non-aces. So I multiply those together. 4 times 1,128 means I have is 4,512. So my event space is 4,512. Now you might say that's a lot of ways to get 3 aces and 2 non-aces, but when I think about the fact that that is out of almost 2.6 million different hands, this is going to be a really low probability. So I'm going to go ahead and take this and divide by 2,598,960. Okay, 0.0017. So the probability of 3 aces is 0.0017, or if I move the decimal point over 2 spots, that is a 0.17% chance, which means you have a less than 1% chance to get exactly 3 aces in the hand if I deal you 5 cards. Odds not very high, obviously. A pretty unlikely scenario that you get exactly 3 aces, but there you go. Okay. So this problem is a lot more involved, takes a lot more work, and quite a bit more thinking as well. That is going to wrap it up for 11.2. Again, some of those earlier slides we're going to actually do in class, and we're going to run some experiments to see the probabilities. But hopefully the idea between experimental and theoretical probability makes a little bit more sense.